Assessing residual fatigue life of old railway steel girders is an essential requirement now for Indian Railways bridge professionals for bridges on 40-plus annual GMT routes and for bridges which have served for more than 50 years. This video will provide a good understanding on this subject. In this video, step-by-step method will be explained to calculate the residual fatigue life of railway steel bridges. First procedure will be explained, and thereafter, with the help of a sample calculation, we will see how it is actually calculated. This is applicable for all kind of railway girders, including plate girders, composite I-section girders, and open web girders. Although the video content is complete in itself, but it would be better if you have some background in the fatigue-related basic concepts like SN curve, detailed category, construction detail, etc. For that, you can watch another small video available on this channel all about bridges. You can watch this by clicking the link which is being popped up on right upper corner of your screen, or otherwise, we are providing the link of the video in the description. Now coming back to the topic, that is the assessment of residual fatigue life by simplified approach. Let's first understand what is meant by residual fatigue life of a railway steel girder. The residual fatigue life of a steel bridge girder refers to the remaining time the bridge can safely operate under a given actual GMT traffic before fatigue failure occurs, duly considering its current condition and past loading history. It is essentially an estimate of the remaining service life of bridge considering fatigue. As per ACS 42 of Indian Railway Bridge Manual, the bridges which are en route having annual GMT of 40 and above, and which have completed age of more than 50 years, shall be systematically assessed for residual fatigue life and will be planned for extensive monitoring till retrofitting or final replacement. For this assessment purpose, a simplified procedure, given in Clause 14 of Appendix-G of IRS Steel Bridge Code, is used. Simplified approach of fatigue assessment is used if actual field measurement or detailed analytical analysis is not done. It is used to assess the first-hand residual fatigue life as a first measure in this direction. The basic formula which is used in the simplified approach of fatigue assessment is to satisfy that incidental stress range multiplied by damage equivalent factor lambda should be less than or equal to detail category divided by Gama MF. Now we will see these terms one by one and how these are calculated. To begin with, the first step is to calculate the incidental stress range, which a structural member is subjected to. In simple terms, it means the algebraic difference of maximum and minimum stresses that are generated in a bridge component when load is passed over the girder. For this purpose, algebraic difference of maximum and minimum stresses is calculated, which means we have to take care of nature of stresses like compression or tension. The stress range for each individual component can be easily calculated with the help of a stress sheet, which is an essential part of the structural drawings of a railway girder. In all RDSO standard drawings of railway girders, stress sheets are essentially given. If it's not available for some old non-RDSO girder, calculations need to be done. Please note that as per Clause 6.2, for fatigue life assessment, only live load and associated effects, such as dynamic effects, centrifugal effects, longitudinal loads, and racking loads specified in bridge rules shall be considered. Please also note that, for fatigue assessment, 50% of the impact loads specified in bridge rules shall be considered. The next step is to calculate damage equivalent factor lambda. As per Clause 14.6 of IRS Steel Bridge Code, Appendix-G. The equivalent factor for railway bridges should be determined by the equation lambda equal to lambda 1 multiplied by lambda 2 multiplied by lambda 3 multiplied by lambda 4. Here, the maximum value of lambda can be 1.4. Lambda 1 is a factor that takes into account the damaging effect of traffic, and it depends upon the base length of the longest loop of the influence line diagram. This lambda 1 basically depends upon the bridge configuration and the train configuration. For this purpose, influence line diagrams for various components of a bridge are drawn, and the length of the longest loop is found out. Once we find out this length, the value of lambda 1 can be obtained from a table given in IRS Steel Bridge Code, Appendix-G. As per Clause 14.6.2 of IRS Steel Bridge Code, Appendix-G for simplified analysis, the maxima for each length category could be adopted, meaning thereby that we should take the maximum value. Next damage equivalent factor is lambda 2, which is a factor that takes into account the annual traffic volume in million tons. Lambda 2 formula is given under Clause 14.6.4 of Appendix-G. It is calculated as per this formula. Here, TA is the annual volume of traffic expressed in million tons. Next factor is lambda 3. Lambda 3 is also a damage equivalent factor, which is dependent upon the design life of the bridge. The more the design life, the more the value of lambda 3. The value of lambda 3 can be calculated by the formula given here. Here, LD is design life of bridge in years. Next factor is lambda 4, which is applicable only in those cases where more than one track is situated on the bridge girder. The formula is given in paragraph 14.6.6. In most of the cases of Indian railways, the bridge girders are for single track. Now coming back to our basic equation, we have discussed stress range and lambda. In the equation, the next factor is permissible stress in fatigue. Basically, permissible stress in fatigue is nothing but the detail category of the member. This detail category is dependent upon the type of construction detail by which that particular component has been built. It is obtained from the Table G2 given in the Appendix-G of IRS Steel Bridge Code. The value given in detail category column is basically stress in Newton per millimeter square if applied to a member for 2 million cycles will result into its fatigue failure. There is a very exhaustive list given in IRS Steel Bridge Code, and we have to choose the matching construction detail in order to obtain the value of detail category. The next and last factor is Gama MF. As per IRS Steel Bridge Code, the value of Gama MF is taken as 1.15. Gama MF is basically the partial safety factor for fatigue strength. The point to be observed here is that the residual fatigue life of a bridge is dependent upon the volume of traffic, the design, life, and years. The bridge configuration, that is, what is the arrangement of various members in the bridge, the train configuration. That is what kind of trains are flying over the bridge and the capacity of the member detail to absorb fatigue effects. If we look carefully, we will find that volume of the traffic is being captured in calculations by factor lambda 2. The design life is being captured by lambda 3, bridge configuration, and train configuration is being captured by factor lambda 1, and the capacity of the member to absorb fatigue effects is being captured by detailed category and SN curves. With this much technical background, we can now come to the steps involved in assessment of residual fatigue life of a bridge. It can be divided into few steps. Step 1. Considering the bridge as new one on present date, calculate fatigue life, capital N years, based upon current GMT for various components of the bridge. Step 2. The fatigue life of the bridge component as on date is capital G multiplied by capital N GMT years. Step 3. Based upon the past traffic data which actually passed over the bridge available with zonal railways, GMT years passed so far over the bridge since its commissioning shall be calculated. Say Gn is equal to G1.N1 plus G2.N2 plus G3.N3 and so on. Step 4. Life left is equal to capital G dot capital N minus summation of all small g dot small n GMT years. With this understanding and technical background, we can now move to see these concepts in action. Now, with the help of a sample calculation, we will understand how to do this residual fatigue life assessment in the real world. Let's take example of a stringer of an open web girder, and let's try to calculate its residual fatigue life. For this purpose, we will use our basic equation for fatigue calculations as described previously in the video. The first parameter which needs to be found out is stress range, delta sigma p. This can be obtained from stress sheet. As we have already discussed, we can find out the stress range of any bridge component from the stress sheet already available in the drawing series. Let's assume for the sake of simplicity that the stress range, delta sigma p in this case, is 50 Newton per millimeter square. The next parameter to be found out is lambda. We know that lambda is the product of four damage equivalent factors, lambda 1 to lambda 4. Now we will calculate them one by one. Let's start with lambda 1. From the stress sheet of open web girder of 76.2 meters span for 25-ton loading, the length of the longest loop of influence line diagram is 7.88 meters. Now from table 14.6.2-1 of IRS Steel Bridge Code, we can find out the maximum value of lambda 1. In the table, lambda 1 values are given for 7 meters and 8 meters. By interpolation, we can find out that the maximum value of lambda 1 is 1.37 for a length of 7.88 meters. Then we have to find out the value of lambda 2. Lambda 2 value is dependent upon the annual GMT traffic, which we want to run presently on the bridge. In this case, we have taken a value of 25 GMT. For this, as per the formula available for lambda 2, the value obtained is 1.0. Lambda 3 is dependent upon the bridge design life in years. In the formula, we will keep the design life, that is LD, as unknown. Considering that the bridge is single track, we can keep the value of lambda 4 as 1.0. Multiplying all these four damage equivalent factors, we get a value of lambda in terms of LD, which is unknown. The next parameter to be decided is delta sigma c, which is basically the detailed category of the component. From the table G2 given in Appendix-G, the detail category matching with the stringer is given as 80 Newton per millimeter square, so delta sigma c can be taken as 80. Gamma MF, as we have already discussed, is a partial safety factor, always taken as 1.15 as per IRS Steel Bridge Code. Now coming back to our basic equation, if we put values of all these parameters, we can calculate the value of LD. In the present case, the value of LD is coming out to be 106.8 years. It means that the bridge component fatigue life for 25 GMT is 106.8 years. It also means that value of capital G is 25 and value of capital N is 106.8 years. When we multiply these two, we get the life of the bridge in terms of GMT years, which comes out to be 2,671 GMT years. At this point, we have to also check that the value of lambda, which we can now calculate by multiplying all the damage equivalent factors from lambda 1 to lambda 4, should be less than 1.4. So now we know that this bridge has a total fatigue life of 2,671 GMT years. Now, if we deduct from this the amount of GMT years, which have already passed over this bridge, we can get the residual fatigue life. For this purpose, annual GMT traffic data available in the division of zonal railway is used. First, we have to add all the GMT years that have passed over this bridge, compiling year on your basis based upon available data. Now, when we deduct this value from 2,671 GMT years, we get the residual fatigue life of the stringer in question. In a multi-component bridge like open web girder, we have to calculate residual fatigue, life of each and every component separately. The residual fatigue life of the bridge is governed by the component having minimum residual fatigue life left. It may happen that while calculating residual fatigue life by this simplified approach, it comes out to be negative. It doesn't mean that the girder has already outlived its fatigue life. Simplified approach is a very conservative approach for assessment of residual fatigue life, and it is used to get a very first-hand assessment of residual fatigue life. In case of getting negative residual life, as per this approach, there are further steps which needs to be followed. These steps are very well elaborated in ACS 42 of Indian Railway Bridge Manual. You can watch another video which is available on this channel itself for knowing more about this ACS 42 of Indian Railway Bridge Manual. So this was all about the current topic. Tell us your topic in comment section. Subscribe for more such content.